everybody. I'm Drishti Jain, and today in my talk it's going to be very exciting. All of us are data generators every moment, even right now, be it right in the conference on our laptops, interacting with others of the conference on Twitter, or even the social media browsing that you're doing. And we have Redis, which helps us solve all the difficulties we might have in handling any kind of time series data that we have. So we're going to dive deep into it. There'll be some code as well. So follow along in my talk. To tell you a little about myself, I'm Drishti Jain. I flew in all the way from India for the conference today. I'm very excited to be here. It's chilly, but the conference and everybody just makes it up for it. Everybody, there's great networking going around conference as well. That is very interesting. Along with being a computer engineer, I'm a core software developer. Along with that, I'm also a social entrepreneur. I have a non-profit organization back in India. We are 400 plus volunteers strong and impacting 11 cities in India. And I'm also an international tech speaker. I like to share my knowledge with the community any chance that I get. And I also have my own initiative called Skill Up with Drishti, wherein anybody who's looking to level up in their career or coming from a non-tech background into tech can just find my calendar link using on my website and book an appointment with me and have a one-on-one chat with me. And yeah, that's my Twitter handle. So you can follow me along there as well. A lot of cool conference interactions that I have, even here, are out there on Twitter. So let's look at the big data ecosystem. If you see, big data is something that we generate each and every moment, be it any kind of clickstream data through social media scrolling that we do, structured data, unstructured data, quasi-structured data. Quasi-structured data is the clickstream data we generate whenever we are scrolling through any of the applications. And across in the big data ecosystem, you'll see that there are 4 major parts of the ecosystem. Right from the data devices, so any kind of data device, be it your GPS tracker, be it your mobile phones, any kind of device that can generate data, that is giving you information, is generating data on its own. Then the second part is data collectors. So right from retail to finance to the government, any kind of, say, taxes you're filing, everybody files taxes. Based on their geographical location, the laws are different. But at the end, you're interacting with the government. You're giving in your data. So these are different data collectors which have tons of data which can be analyzed and is being analyzed to optimize, create new features, and make the process more efficient. The third one is data aggregators. So right from organizations in the advertising world, they collect data and they're able to aggregate this data to form something meaningful which can have a monetary business value. So the reason why data is the currency of the future and of now is data can be used to sell products to people. And once something can be sold, there's revenue involved. And that is what is driving all the ecosystem across data. And people want data aggregators. They want as much as analysis and as much as things that they can do with data right on their fingertips. And last but not the least are data users and buyers. So there are great GDPR laws in the EU, but for the rest of the world, the laws are not that strict. So there are a lot of data buyers out there who can use data. They can buy data from data aggregators because the person who has created the data, say us users, have allowed it in the terms and conditions that we signed up for when we are using the app or when we are downloading anything from the internet. So data buyers is media, any other services, right from even law enforcement to employers. There's a reason why if you go to many places, even if you are, say, visiting the mall and you somehow given your data for some particular course or you signed up for an online course somewhere, and the policy there was that they are able to sell it to any kind of data buyer. And then you'll keep on receiving a lot of job listings, or maybe you could even get a call from one of the recruiting department members. So how does that happen? It happens only because they are able to sell the data that was generated. So this gives you a broad idea of how the big data ecosystem is there and how does it actually is very much integrated into our everyday lives. Say even when we take the tram or the bus to the conference venue. So if you're using Google Maps, you as a user might also give feedback inside the Maps feature if the tram was crowded, if it was empty, if there was space to stand, did it run on the scheduled time, was it a minute late, was it a minute early. So all of that is also data which is being used to also benefit the society. So the government who runs the tram will get to know if there are peak hours, so they can have more tram services. And if there are hours when the tram is mainly empty, so they can also reduce the cost that at the end taxpayers pay for efficient running of the trams. So all of this is where big data is created and used very frequently. Now, when we talk about so much of big data, there's of course challenges with anything that involves a lot of variety, a lot of velocity, and a lot of volume. So these three are the main features. And the focus that I want to bring on is about any kind of time series data that we create. Time series data is going to be every second you're collecting data. If you have a sensor which is taking in the AQI, the air quality index, it is going to collect data at the set intervals. It's going to be, the size of data is going to be so huge, the volume is going to be continuous, and you would want to store it in order to analyze the air quality index. So in all cases like this, there are a ton of challenges that come with it, especially with volume. Any time we deal with scale of data, we have to tackle volume with which the data is created. The velocity is the speed at which it is generated. So if we continue the example of sensors, say the speed, if it is a factory setting, the speed at which data gets generated can increase based on the production speeds that the factory is generating material on. These sensors may be used to calculate the heat of the boilers. It could be used to calculate the current pressure or record the current pressure, record the current temperature of the different boilers. And when it is in production, there's going to be a lot of velocity of data that we will have to handle, and variety of data. So whenever we are dealing, especially in the world of, say, social media or anything that is online on the internet, there's going to be variety of data. As a user, say any social media site, I'm going to be creating textual data. I'm going to be posting photos. I'm going to be posting videos. I would be posting GIFs. It's going to be a ton of things. So the variety is also something that has to be handled. Now, once we have been talking about data and especially time series data. So to keep it simple, you can just think of time series data as data associated with a timestamp. That will give you context of everything that I talk about. So any data that you create, there's a timestamp associated with it. So it could be very frequent data, it could be at specific intervals. In general, time series data is data which has a timestamp associated. Now, once we handle this with Redis, there are existing Redis data structures as well that can be used. So say, if I talk about sorted sets or I talk about streams, both of these are existing Redis data structures. And of course, they can be used to handle time series data. But there are a ton of challenges that come with it. And the reason why we shift to Redis Time Series will be more clear once we see what are the challenges with sorted sets as well as with streams. So for example, with sorted sets, it stores the values by their scores. And in case of time series data, the score is going to be the timestamp of the data that we have generated. Whereas in case of streams, it is still better, being a more recent data structure and has better capabilities as compared to sorted sets. But still, since it was designed as a generic data structure, we don't have all the capabilities to handle time series data specifically. The major downside is of sorted sets is the efficiency. The time complexity is very high. Insertions itself take log n time. So that makes it not an efficient process when we have to handle huge volumes of data, when we have to work with continuous stream of data, analyze it, store it, perform visualizations on it, integrate it with other tools and use data to its capability to identify the results that we want. So that is wherein anytime you want to work with tons of data, Redis Time Series is what comes to our rescue. Redis Time Series provides us tools which we can easily integrate and use it to handle any kind of time series data. Now, as I'm talking about time series, Redis Time Series, let me just quickly touch upon what a time series database is. So a time series database is a database that is optimized to handle and store time series data, and it has capabilities of more efficient storage and retrieval of data that is of the time series type. Because we are going to have a set of data points which are going to be created continuously with timestamps, it is important that we have specific databases which handle this kind of data. We cannot just rely on our traditional databases and then just keep on engineering it more and more so that it is able to efficiently handle time series data, which since the past few years has been more prevalent in any commercial setting. And Redis Time Series is a Redis module. So it has capabilities of Redis. It is built with the positive parts of Redis and also has the capability of actually working with time series data, giving us very quick functions, very easy to learn, very intuitive, of creating different rules, of adding structures, time series, everything. So coming to what time series, Redis Time Series is. So it is a list of memory chunks. So the way data is stored in case of Redis Time Series itself is different. It is stored in the form of chunks. And each chunk has a predefined size of the samples. Each sample is a 128-bit tuple with two parts to it for the timestamp and the value, so 64, 64 for the timestamp and value. This makes it very easy and very intuitive for us to understand how time series would be stored. So we have a value, we have a timestamp, we store it together, divide our chunk into equal parts and store it there. Now, this time series data can be of different types, be it if you want to analyze stock prices, you want to see where the market is going, you want to analyze, say, vehicle movement for a traffic management system, or if you are working with any kind of sensor data. It could be related to environment, it could be related to patient data, it could be related to some medical device which has a sensor which is actually helping a patient who underwent surgery. So any kind of data can be handled very, very well with Redis Time Series. Now, there are four main characteristics of time series data. The first one is that it has a high speed data ingest. So the frequency at which we are going to get data, which is of the time series type, is going to be of a very high velocity, a very high speed. So it is important that our database, our time series database, is able to handle it. Imagine every, so we'll also be optimizing this example further down. So imagine you are collecting data every day for a sensor, and even sometimes you're collecting every half a second, sometimes during the day in a 24-hour period, you're collecting data every minute. Then in the peak hours, you're collecting it every 30 seconds, sometimes every 15 seconds. It could create billions of data points for one particular day. But consider a case, say 10 days or even say a month later, when you want to analyze your historic data, would you actually want to have those 1 billion data points per day and actually pay to store all of that? And also, if it is only stored as raw data, it is going to be very difficult to actually go ahead and analyze, make sense of that data, and look at it in a broader picture. So there are interesting features we'll be looking at further down the line, but this example is something you should think about. How would you actually work with data wherein you're creating billions of data points every day, and you have to also think about it, say, from a year now, a month now, a year now, so that this data is very useful to you. With that thought, continuing on the different characteristics of time series data. The second one is immutable data. So any sensor data, if it is giving you a reading, say the air quality index at this timestamp was this, it is going to be that. You're not going to change it. So there's going to be a lot of data that you have to store. There can be a ton of unstructured labels. especially in case of sensor type data. Depending upon the domain of the application of sensor, it is going to be very, very different. In healthcare, there are a ton of sensors which are also inserted in a patient's body if they undergo some major accident. So there is very complex data which could have different unstructured labels. That has to be handled, and it is also going to be a time series data. There's going to be time associated with this unstructured data that we have to handle. And the most important part is that we want this data to be future proof. I call it future proof, being that time series data is going to take us places. It is what is going to help us analyze our historic data, but we also have to act very quickly. It is not that we can sit and spend days to analyze it. It has to be future proof, that we can derive insights, move it to the current world, and work upon it. So aggregated summary of data for time series is very important. So this is all such a big complex problem that Redis Time Series is solving it for us. So let me show you how would you try Redis Time Series data on your own. So you would, to try out Redis Time Series, you would directly launch your instance using Docker. You would launch your Redis instance. Then there's a pre-compiled version on the Redis download source as well that you can directly go and run it. And next you would clone the Redis Time Series repo, and you would run your Redis with time series. You would make your setup, and that's it. So it is as easy. Being a pre-compiled version, if you want, you can refer to the documentation and also compile it on your own. But if you want to try it out, say on the go, it is very easy to use the pre-compiled version and run it. And once that is done, in your Redis server, you would load your module for time series data, and that's it. You will have all the features, and if you have ever worked with databases, I'll also be showing the complex tasks which can be done with very quick queries, if you may say, for Redis Time Series. Looking at different features that Redis Time Series allows us to do, it helps us query by the start time, end time, as well as the label set. It also has different aggregated queries. So you can find the min, max, average, sum, range, count, first, last for any kind of time bucket. So in Redis Time Series, every part is chunked, and that chunk is called a bucket. So for each time bucket, you can have any kind of aggregation queries right at your fingertips. You can configure the maximum retention period, which is very useful if you're handling a very high velocity data application, wherein there's a ton of data being generated and very, very fast. So that is very crucial as well. Labels index, so each key has labels, which allows us to query by labels. So this is important when you are working with a lot of data. You have labels associated with each key, and that key has the value and then the associated timestamp. So querying with labels is a very efficient way to find the required data part that you want. And it handles high volume inserts and provides low latency reads. So that is the main core benefit of having Redis. To show you a few of the configuration parameters, configuration parameters for Redis Time Series can only be set at load time, and they're done by appending the arguments to the load module argument. And once you're starting it from your command line, or once it is there in the Redis config file. So there are different commands. Instead of going into each of them, I would show you a few examples with a few of them. The common ones, say add, create, delete, info. These are very interesting. Yeah. So the TS that you see, that is that like indicates time series. So in Redis, you can do everything with TS dot, and based upon the commands that you want to use, based on the specific functionality that you're working on, you can use it. Be it if you want to increase it by increase the value of something, decrease the value of something, find the information, all of that can be done using commands. Also, like the regular Redis documentation, the Redis Time Series documentation is very well documented. So anytime you don't actually have to remember, anytime you have a particular use case, you can go there, search for the keywords, and you'll find the corresponding command, and that will make it very, very easy for you to start working with it on the go. You don't have to spend any time to actually sit and learn about it. With respect to configuration parameters, these are the configuration parameters that come with it. I will be discussing the two main ones, the num threads and the compaction policy. Also, compaction policy is, in my opinion, the best part about Redis Time Series. It helps us do great things and actually tackle time series data. So coming to num threads, so that is the number of per shard threads for any cross-key queries that you have. Obviously, it has to be greater than or equal to 1. You would have at least one number of thread. And it is always not the case, just like in regular complex programming, that if you have more threads, it would be more efficient. No, it could be possible. If you have more threads, it could be less efficient. So finding the right number of threads is very important. And you can directly use, you can append num threads to load module when you are working with your Redis server directly. So it is very easy and very intuitive to actually set the number of threads that you want. Just don't think that if you increase the number of threads, it would make it more efficient. There is always that optimal number of thread count. It might be possible that very high number of threads would actually go against the concept of low latency and would actually lead to high latency reads in your data. Coming to the most interesting part, the compaction policy. So compaction policy has no effects on the keys that we create with TS create. So you must have seen in here that there's TS create as well as there's TS add. So add and create are two separate functionalities. Any default compaction rule that you want, you create it, and that has no impact on create. We are going to see another function called create rule. So in case of create rule, what happens is you have to first create, and then you create a rule on that. So what compaction policy allows us is, if anytime you're creating it with .add, the policy would apply only to add. So if you want to have something without the policy, you can use TS create. And if you want to have something by default, then you can define the compaction policy. You would define it something like this, and once you define it, it will work only on ts.add, not on create. Just to explain what this complex thing looks like. So the max 1M, 1H that you see, so I'm trying to aggregate my time series data over 1 minute and retain it till the last hour. So it is very similar to how we understand regex expressions. Just a few tries with it, you'll be an expert in it. So the first part that you see of max 1M, 1H, that is that I want to aggregate using max, the maximum of it, for the 1 minute and retain it till the last hour. And accordingly, I have other compaction policies defined anytime I'm using .add. Now, since with time series data, especially any kind of sensor data that I have been talking about, there's going to be a ton of data generated. Imagine this is the graph that looks like of all the data points that I have, and that is all there as the data that I have collected. But 1 month from now or 1 year from now, I would want to just have key points from this data. How would I actually do that? How would I actually downsample or compact my data? So we want to downsample it only when the less fine-grained data, whenever we have to look back at it, it is not very relevant to the use case that we are working in. Take the example of, say, air quality index. It is okay to know that from 10 a.m. to 12 p.m., the air quality index was, say, 10. But for me, maybe 1 year down the line, the use case is not very relevant to have each hour or each minute air quality index. I would just like to know the average to understand how the trend in the air quality pollution has been. In that case, downsampling is very useful. Also, whenever the fewer historic data points are required for raw data, we can go ahead with downsampling. So the graph from, this is like before downsampling to after downsampling. So we would, effectively, we have 10 data points in an hour. We are compressing it, finding some logic so that the 10 can be converted to a single data point. And that logic is my aggregation function in Redis Time Series. So just to have a mental model of it, 10 data points to 1 data point, and how do we convert it is aggregation functions. And that is a great benefit of Redis of providing the ability to downsample or make it compact. Say this is the syntax of creating it. So ts.create rule. You would have your source key, destination key, aggregation function, and the bucket duration. So taking in the example I asked you to think about during the first part of my talk of, say you have 1 billion data points in a day, and you need to work with it further down the line. So you need to also manage the huge amount of data that your sensors are collecting. So how would you do that? Consider the case of pollution in a city. We have collected 1 billion data points during a day, and now we have to reduce it to a manageable amount of data point, which can be finally stored with us and used in historical analysis anytime in the future. So I can reduce it per minute. So I can have, instead of say 1 billion data points for the day, for every minute I can have 1 data point associated. That would effectively be, so 24 hours would lead to 1,440 data points, which is so less as compared to 1 billion. So that is the benefit of having downsampling and compaction. So 1 billion data points converted to just 1,440 data points is a huge downsample, and we are still able to retain important information. And remember, this is only useful when raw data, like exact data points, are not very necessary. In an application like weather or meteorological related applications, this might be useful. But in case of medical, we would have to have more number of data points per day for any kind of sensor that is there with the patient. So now how does this look like? So the top one is the syntax that we looked in a few slides ago. So my original sensor name is pollution sensor, and my destination is the compacted one. So pollution sensor compacted, and I'm using aggregation of the type average. I'm averaging it per minute, the number of data points that I have, to have 1 data point per minute. So I have AVG average and into 60 seconds or 60,000 milliseconds. So this is going to create the rule across all of my pollution sensor data, and my output is going to be in my pollution sensor compacted, and it will have, the end result would be that my pollution sensor compacted would have 1,440 data points only, instead of my original 1 billion data points. So you see, this is a huge impact in any time we are handling any kind of time series data, and it is so easy to implement, very intuitive. Just like, I think I can compare it to SQL. Most of us start learning databases with SQL, and using obvious terminology like AVG for average is very useful, and create rule gives you the sense of what is the aim as well. So create rule is creating this rule on anything that you use with ts.create. This is, I think now it is more clear for you as well to understand why ts.add could have a policy, a compaction policy. So anything you're doing with that would automatically have the policy invoked. So it's like the default policy you're implementing on it. But whenever you're creating a rule, you would actually first do ts.create pollution sensor compacted, and then write ts.create rule and the whole create rule part of it. So that would work only on the ts.create that is there. Now, Redis Time Series is very impactful. We saw how it was able to reduce our 1 billion data points to 1440 data points. And now there are a ton of integrations that can be done of Redis Time Series with everything that we love already. So be it with Grafana, be it any kind of Prothemus alerting that you want to do, it is very easy to integrate. You can have it all in a good visual form in your Grafana dashboards. And with your Redis Time Series adapter, it is very easy to integrate. You directly import it, and it is able to do it. Just to show you an example with Grafana. So there's a Grafana Redis data store as well. That's the GitHub repo. You can head there and explore more as well. So Grafana and Redis Time Series work very well, and that is generally the industry standard being followed by a ton of developers, a ton of engineers out there, because Grafana is already something that is used in most organizations. And when handling time series data, you just have to know about handling Redis Time Series and integrate it to your Grafana dashboards. Talking about Redis data source for Grafana, it is as easy as you would work with any of your Grafana dashboards. You would work with your huge amount of Redis time series data that you create, use the Redis data store for Grafana, have dashboards, have interesting visualizations, and go ahead, create more data. And any queries that you define, like the one we discussed here, and this is one of the most important parts of working with Redis time series. And what this will help you do is create like amazing visualizations, work with a ton of data. And the more you try out things, your aggregation functions is something which can help you play with your data very easily. Like I use the example of taking an average for per minute. There might be some other logic that you want to use. Maybe you want to take the maximum of that per minute, and that is enough for the application that you're working on. Or it could be a case that the minimum would be more relevant. If you are looking at, say, the glacier melting, there's glacier 3000 so nearby to Geneva. And if the record of data is being done of the amount of the size of glacier that is melting over time, maybe a more better aggregation function would have been to take the minimum for all the data points of the length of the glacier or the ice and take the minimum of it to understand the reduction. So it completely depends upon the application that you have. And that is wherein we as humans, we as developers use our intelligence. And that is something that comes with the domain expertise of what domain you're working in, what is the actual application of the data, the time series data that is out there. So just taking an example as well. So if I have to analyze, say, a simple example that you can also try out, with the stock market, you can take in two stocks and compare the performance of stock prices using a Grafana panel itself. And you can have your own queries, which can be Redis time series data. Stock prices is the easiest example you can start and try out in order to understand how time series data works. And because stock prices change every minute, so you have a lot of data to play with. There's a ton of things you can do. You can you can also work with creating, like you can look at external economic factors and how it is impacting stock prices. So you can have two different data points. You can have the news and the timestamp of when the news was, any kind of news related to a particular company was there, and how did it impact the stock price? Was there a delay in it? How did it look like? So there's a ton of time series data that you can work on with it. Now, this has been all about the great parts of Redis time series. Now, a very complex issue that Redis time series also handles is any out of order or backfilled ingestion performance considerations. So anytime there is a new data point which was, say, missed, there were 10 sensors that were monitoring things, and due to some reason, one of the sensors was not able to communicate back the data to us. But after a day, we got that data like physically, because it was being physically stored at the location, and we want to insert that back. But we are already on the next day. So this data is also being generated. So how do we handle that out of order data ingestion? Because that could be the game changer in the analysis that we do in any kind of Redis time series or any kind of time series data. Maybe that sensor was actually impacted due to a sudden change or fluctuation in values, and that is going to actually change the way we model our things. So any older timestamp, whenever it is inserted to a time series, is wherein we face the issue of out of order insertion of data. And the chunk of memory corresponding to the new samples time frame has to be retrieved from the main memory. And imagine that you had already compressed the previous day's data. Now, say the compression of all the data is already done. You're say every minute you have some logic to reduce the data points to a single data point, and now you have to insert this there. And it could have an overlap between two different instances. It need not be very direct of just averaging this out and inserting it in the data of the previous day. There might be instances of actually decoding a compressed chunk, adding this data there, recalculating that chunk, compressing it again, and then using it across our data. And this is going to be very memory intensive, and whenever we are decoding any previously compressed chunk of data, it is going to be very compute expensive as well. We have to have policies defined, algorithms defined in order to decompress as well. And of course, it is going to be compute intensive, and that is something that has to be handled as well. And this is handled by Redis Time Series very well. Yeah, the graph is visible. So if you see here, so if there is a 5% out of order, the yellow line is the 5% out of order, the red line is 1% out of order. So if there's only a very small percentage of data that is out of order, which has to be inserted back to our previous or our already compressed data, then it is comparatively easy. But as your percentage increases, as more chunk of data has to be inserted back, you would have to decompress a lot, a bigger chunk of the previous calculated data as well, and then insert this data and recompute or recompress the time series data in order to retrieve the values. As a rule of thumb, to increase out of order compressed performance, you should reduce the chunk size as much as possible. So this would lead to smaller chunk sizes, but the number of chunks would be a lot more. So there has to be a good balance between the kind of application you have, the possibilities of out of order memory insertions that you can have. As a rule of thumb, a simple one rule of thumb to solve this is to have smaller chunk sizes. So you have to only deal with very less out of memory insertions, because it could be possible that only one chunk is going to correspond to that particular timestamp. To put it in context, say from a minute, if you have 1 minute divided into 4 chunks, so 0 to 15 seconds, 15 to 30, 30 to 45, and 45 to 60, and the out of memory insertion that you have was for a timestamp of 15 to 30. So in that case, since this is already a chunk, you would decompress this chunk, insert this data, and compress it again. Whereas if this was a 1 minute chunk, 1 minute would have been compressed, you would have to decompress that. It would require a lot more compute power, then insert all of this data back again, and then compress it again. So it's always better to have smaller chunks, and smaller chunks imply less computation on double data decompression. So whenever you have to decompress, then insert data, compress again, so it is like a double compression that you're going to do. So looking at this graph as well, the more number of out of order percentage insertions that you're going to have, so it's better to have lower, a lesser size of the chunk. It will lead to more number of chunks, but it is better to handle any out of memory insertions. This is especially useful wherein the physical environment conditions of any sensor can be impacted. Say if the sensors are located in a glacier or a snow setting, or they're in like very less accessible areas, say valleys of mountains, and it is difficult, only there's going to be one maintenance person who would go say every week only to check. So you would have 1 week previous data that you would have to handle if you're going to do out of memory inserts. So it depends. If you have an extreme case like this, or even if there are big boilers, if there's like a big industry application of a chemical factory, they have big boilers, big instruments which have sensors in it. And since many sensors are located inside the boilers, so only at the maintenance schedules will those sensors be checked. We would only get to know that they're malfunctioning, and of course it will be fixed at that point, but maybe data is being physically stored, but maybe not communicating well back to us. So in that case, having a smaller chunk size is much, much useful. Yeah, and Redis also provides aggregation at read time. So just like all benefits of Redis, it is very much at the read time that we have aggregation. So whenever you have to query a time series data, if you have to do it ahead, it is going to be cumbersome to stream all data points if you are only interested, say, in one particular hour of the day. So Redis Time Series follows the Redis philosophy and transfers only the minimum required data so that you are able to query your database very well. And so aggregation at read time would look something like this. If you have buckets of 500 milliseconds with an aggregation function like this, you would whenever the aggregation is there, you would retrieve data only of that particular time, work with it, and that is what will give you the desired results. So working with Redis and utilizing Redis Time Series has all the capabilities of Redis. And since it follows the philosophy of Redis as well, we are able to do aggregation at read time. So to summarize, Redis Time Series helps in big data analysis tremendously. Time series data is something we can no longer escape. Maybe, say, some time ago, there were not a lot of applications which required very time-sensitive data in everyday user data that is collected as well. But now, whether it is an application which has sync across devices, whether there is an application which is going to monitor a user, the behavior of a user, maybe the application is nudging the user to buy a particular product. So the data is created at every time stamp that you can think of, to understand the user behavior especially, because that is where the world is leading us. We get advertisements, and maybe a month later, we are more inclined towards buying a car, whereas we had no plan of buying a car in the first place. So all of this data is time series data, which is used in varied applications. And Redis Time Series is going to help us there. To go through a few applications of Redis Time Series, the very first one being healthcare. So healthcare is a very, very big domain wherein Redis Time Series is being applied by a ton of big corporations, be it valves, be it sensors in the medical devices, any emergency medical facilities as well. The sensors are going to produce a ton of data, and especially in medical field or in emergency medical healthcare, it is very, very important that the data is collected frequently and it is analyzed. We are able to handle time series data very well as well. It should not be a case that we have sensors, but we don't have a way of handling time series data. So that is a lack on our part if we are not able to handle the data that is created in the current world. The other part is finance, be it right from stock price analysis, or be it in the insurance space to understand how things are working. With COVID a few years ago, insurance companies saw a lot of boom in time series data. The number of claims people were applying for in insurance companies had to be handled by them very well. They had to modify policies, bring in new policies, new coverages, have people pay a little extra premium to have things like COVID included. So there was a lot of time series data collected from the users and then applied in a commercial sense in the healthcare, in the insurance space as well. In agriculture, so with farming especially, or especially with the rise of organic farming, every sensor is very important to understand if the produce is being grown correctly or not, if the soil water content is right, if the nutrients are right. So all of this is time series data which is used, and especially in organic farming, this is used very often to understand if the produce will be grown correctly, if there's some pest impact or something happened to the soil, and that has to be taken care of. Because organic farming is comparatively more expensive on the producer side. They do charge a premium for it, but they also want to optimize their growth, their produce growth. For traffic monitoring, with the rise of the population in general in the world, traffic is becoming a more and more concern everywhere. So time series data is collected at every traffic junction, and it is analyzed not just for the traffic movement. It is also analyzed to understand what kind of vehicles are there, and that helps us understand the purchase power of that demographic area. So traffic monitoring has very different applications that a ton of startups are also working at. So you would think that the data collected at traffic monitors would only work to understand if there's peak hour time, non-peak hour time. But that is also used to understand what kind of ads should be placed at those places. If it's more of a luxury car kind of segment, then that audience would be targeted. If there are more people using public transport, then more things would be targeted. Maybe they would target having ads inside public transport. So they will understand what places their advertisements will give them a better return on their investment. And weather forecasting. Any meteorological implementation, understanding the environment around us, or simply understanding the global warming impacts, be it the glaciers melting, impact on the water sea level, every weather related or every meteorological department related application has been using sensors since forever. And that analysis helps us to understand if it would rain today, it would be sunny, and that also has other implications of understanding any kind of rough weather which could impact population in the health space as well. So weather forecasting with health impact is something that is used a lot, and that is wherein we create a ton of time series data. And actually meteorological department or applications like this is where time series data has been handled very well since a very long time. It is only now since say 4-5 years that everybody is realizing the importance of time series data to be applied in a more commercial sense for each of the users in our everyday lives, to make us or to nudge us to buy a particular product or target ads towards us such that we are buying one brand over the other for the same product. It could be possible that the ingredients are same, but also the advertising world also uses a lot of time series data to understand how the user behaves, what are the products that the user is going to be more interested in. So they would also change their advertisement to focus on selling you the product through different parts. Instead of just saying that it is eco-friendly, they would maybe say that it is it does not have a particular chemical in it, because maybe you were researching a lot and the demographic near you was researching a lot on avoiding use of that chemical. So it is very complex insights that can be derived with time series data and anything that we work with. To share the references and attributes across my presentation, this also, so the first and the last one are the Redis.com and Redis.io documentations. So you can directly go there, look at time series, use it everywhere. Redis Time Series is changing the way and making it very easy for us to handle time series data, create good analysis, and have integrations like with Grafana, and have interesting dashboards which can be useful for us in sharing the whole concept or the whole knowledge that we have gained from time series data with the stakeholders in our organization or the project that we are working on. So any integration like this with Redis Time Series with Grafana is going to be very, very useful. So yeah, that's from my end. I hope you go ahead, try out Redis Time Series. Many of you must be core Redis users and powerful Redis users. It's now time to actually go ahead, use Redis Time Series, make the most of it, and derive insights. Maybe start your own personal project wherein you are analyzing some publicly available time series data through the, so most of the government portals have a lot of feed of live time series data. You can use that, create some application of it on your site, and maybe that could turn into a huge revolutionary product. So I leave you with that. Go ahead and use Redis Time Series and make an impact.